All right, guys, so today we're going to be looking at expectation algebra, which means we're going to be dealing with expected values and variances and dealing with combining them, mostly in linear manner, but you'll see kind of as we go on the different ideas that we're going to be looking at. All right, so I've got here a random distribution, right? You can see that this is a distribution function. I've got 0.1, 0.2, 0.3, 0.3, 0.1, which do add up to 100% or 1.00, and it's not a binomial distribution or a Poisson or anything like that, though this thing that we're talking about will also work for those types of distributions. All right, the first thing we're going to do is we're going to draw a bar graph, because I want you to see what this looks like if we put it on a bar graph, because this is going to help us as we kind of go through reasoning through our next steps. All right. So let's go ahead and put it on. We've got 1, 2, 3, 4, and 5. And then with the probabilities, we need to go up to 0.3, so 0.1, 0.2, and 0.3. So 1 went up to 10%, 0.1. 2 is going to go up to 0.2. You could put this together if you wanted, kind of more histogram style. It doesn't really matter. I think it'll be fine. 3 will go up to 0.3. Okay. And then 4 will go up to 0.3. And then 5 will go up to 0.1, just like that. So there's our bar graph. All right. Now, the first thing I want us to do is let's find the expected value of x. All right. So expected value of x, which we know all we need to do is take each of the x values and multiply it by its probability. So 1 times 0.1, which will be 0.1, and then 2 times 0.2, which will be plus 0.4, 3 times 0.3, so that's 0.9, 4 times 0.3, which is 1.2, and then last of all, the 5 times 0.1, which would be plus another 0.5. Add all those together, and we get an expected value of 0.5, 1, 2.2, 3.1. 3.1. All right, awesome. So easy enough, right? But my question now is, what would happen if we did this? What would happen if we did the expected value of x plus 3? Meaning that we're going to add 3 to every single one of our x values. All right, so this one, instead of being 1, is now going to be 4. This one, instead of 2, is now 5. This one, instead of 3, is now 6. This one, instead of 4, is now 7. And this one, instead of 5, is now 8. What would happen to my expected value? Well, it should add 3 to every single number, right? And if I add 3 to every single number, then the expected value should go up by 3. I should get an expected value of 6.1. Now, you can test this out if you want. You can do 4 times 0.1, 5 times 0.2, 6 times 0.3, and so on and so forth, and check to make sure that that's right. In fact, I encourage you to do that to see that Mr. Bauer isn't just lying to you again. And not again. Mr. Bauer hasn't lied to you before. He has made mistakes, but he hasn't lied to you. So you can, but yeah, check it out. See if it works. All right. How about this one? What if instead of adding 3 to everything, no, looks like it's not going to let me delete that. Oh, that's not what I want to do. All right, what if instead of adding 3 to everything, what if we multiplied everything by 4, right? What if these are sizes of juice bottles and we decide that we're going to make our juice bottles 4 times bigger? All right, what then would we expect? What would be the expected value if I take all of my x values and multiply it by 4? Well, let's see. This one, instead of 1, would now be 4. This one, instead of 2, would now be 8. This one, instead of 3, is now 12, 16, and 20. Okay, now the adding one was pretty easy to say, yeah, all you do is add 3 to everything. The average should go up because the average is the middle of all the numbers, and all the numbers just shifted up, right? Well, how about this time when we multiply everything? Is it really just going to multiply my expected value by 4? Well, let's see. 4 times 0.1 is 0.4. 8 times 0.2 is 1.6. 12 times 0.3 is 3.6. 16 times 3 is 4.8. And 20 times 0.1 would be 2. I add all those together. I've got 2, 4, 8.8, 12.4, which is the original one times 4. All right, so basically what we've just discovered is that, let's get another color here, is that if I have an expected value, all right, and then I transform that expected value by multiplying the x value by a number and adding it, okay, that my new expected value is going to be the same thing as if I had just multiplied that number times my expected value and then added whatever that number was on the end. Okay, and that's what we just saw. Okay, now what I'd like to do is take a step back and see if we could consider what would happen to the variance, the spread. All right, so let's consider, we're not going to solve for the variance, okay, but let's consider if we had the variance and we had a specific value for the variance, what would happen if I did this first scenario right here where I add something to every single value? Well, hopefully you recognize that what happens in that scenario is that it goes, the first one isn't at 1 anymore, so there's 1, 2, 3, 4. The first one is now at 4, which goes up to 0.1. The second one's at 5, which now goes up to 0.2. I'm not labeling my y-axis because I just want you to be able to see. So then we go to 6, right? And I'm using the blue numbers that were up here above, 4, 5, 6, 7, and then 8. Okay, look at the spread of this compared to the original one. The spread is the same, right? We just took the whole graph and we shifted it over 3 spaces. So what does that mean about the variance? Well, that means that if I multiply the x value, multiply this random variable by something, the variance doesn't change. Or in other words, the variance of a times x is the same thing as the variance of x, right? Sorry, that was not multiplication. I am lying. No, I'm not lying. I made a mistake. The variance of x plus a number, sorry, is still equal to the variance of x. All right, now let's look at the other scenario. What happens if I multiply everything by 4? Okay, well, let's draw a picture. Okay, before it was at 1, 2, 3, 4, 5. Now it's at the green numbers, so 4. So 1, 2, 3, 4 is at 10%, 0.1. 5, 6, 7, 8. 9, 10, 11, 12. Sorry, 12 is in the wrong place. We'll do that. So it goes up to 0.3. 12, 13, 14, 15, 16, 17, 18, 19, 20. Now what do you see? Now we have a significant amount of spread going on, right? These bars are much more spread out than they used to be, all right? Now we're not going to go through a mathematical proof for this, but what I am going to tell you is that if you take the variance and you multiply it times a times x, right? So you multiply your variable by a number like we just multiplied it by 4, then what that does is it's going to take your original variance and multiply it by a squared. Okay? And like I say, we're not going to go through a proof of this. You may be able to find one in your textbook or online, but it's not what we don't really need to worry about that right now. Okay? So the point of this was to introduce you both visually and algebraically to expectation algebra. What happens when we add values to a random value, multiply? How does that affect both the expected value and how does that affect the variance? All right. So what I'd like to do now is just show you the formulas that are in your formula packet. All right. And that's these right here. Okay, now there's quite a bit of formulas here, right? You'll see the two that we already talked about, right? This one right here, which talks about if you multiply and if you both multiply and add to x, that you can pull out the a and the b and just take your original expected value and multiply it by a and add b. And then we have the one with the variance right here that we talked about, right? Where we said if we add b, nothing happens because that just shifts the graph over. And if we multiply by a, then the original variance will be multiplied by the square of that. All right, so those formulas are in your formula packet. Okay, two other formulas that you see are these down below. Now I'm not going to go into the proof of these, but basically this is just if I add several different distributions together, and I want the total expected value of combining all of those, I can just do them individually, right? Just add the expected value of the first one plus the expected value of the second one, and so on and so forth, right? Same thing with the variance. If I want the total variance of several distributions combined, then I can just do it individually. But again, with variance, that coefficient, if you multiply x by a number, that needs to come out and be squared. And so we can do each one of those individually. All right. So I'm going to show you how those are applied in just a minute. All right. We're going to go through a couple of examples. We're going to go through at least 3 examples and maybe one more after we talk about one more concept that we need to talk about today. Okay. So hopefully just getting comfortable with, you may or may not actually ever use these formulas down here at the bottom. It's more just a comfort with, this is like, you know, the distributive property, or this is like the commutative property. You know, it's just a property that you want to be comfortable with so that you can use it when you're in the middle of a question. All right. This is more of something that you would be indirectly tested on, not something that the whole point of the problem would be this. So let's go ahead and look. We've got a couple of questions that we're going to work through here. Okay, the first one is Richard is waiting for a bus. There are 2 bus companies, the K Bus and the L Express, who serve as bus stop. The numbers of arrivals follow a Poisson distribution. So remember, I mentioned that I made up that distribution, but it works for all the types of distributions that we looked at. So this is an example of one that has a Poisson distribution. On average, there is 1 bus every 5 minutes arriving from K Bus and 1 bus every 12 minutes from the L Express. Richard can use either company to get to his destination. Assuming that the buses arrive independently of each other, find the probability that at least 2 buses arrive in a 10-minute interval. All right, so let's talk through how we would work this out, right? What we want to know is, what is the probability that 2 buses arrive in a 10-minute interval? All right, so we are looking here at 10-minute intervals. All right, and we know we want to say that the probability of 2 buses, at least 2 buses, so the probability that the total number of buses is equal to total number of buses. I'm thinking ahead of myself here. Total number of buses is greater than or equal to 2, at least 2 buses. All right. Now B, of course, here is, and this is where this idea of the combining and algebraic manipulation come in. B is the number of K buses plus the number of L buses. which is greater than or equal to 2. All right, so let's look through. How many K buses do I expect? What is the expected number of K buses that should come by in 10 minutes? Well, it says on average there is one bus every 5 minutes from the K bus. So in 10 minutes, what is the expected value? Well, the expected value of K in that 10-minute period is 2 buses, right? That's what we expect. All right. What is the expected number of L buses? Well, it says 1 bus every 12 minutes. So just like we did with the K bus, and remember with the K bus, we took 10 and divided by 5 so that we could scale it up to the 10 minutes to give us an expected value of 2. We'll do the same thing with L. We'll take the 10 minutes and divide by 12, which then gives us 5 over 6. So what that means is it does say that these are Poisson distributions. So that means that K is a Poisson distribution with an expected value of 2, and L is a Poisson distribution with an expected value of 5 over 6. All right. Now what's going to happen is we're going to put those together, right? We know that the expected value, E of B, is equal to the expected value of K plus L. Now, from what we were just talking about in the previous slides, we then know that that is equal to the expected value of K plus the expected value of L, and that is the algebraic expectation, the expectation algebra that we're talking about. So the expected value of K, of course, is 2, and the expected value of L is 5 over 6. So what that means is that the expected value of B is 2 and 5/6. All right. Now we want to find the probability that at least 2 buses arrive in that 10-minute interval. So what that means is that B is a Poisson distribution with an expected value of 2 and 5/6. So we can answer this question now, right? We can go into our calculator. We can put it into our Poisson. We do want at least 2 buses, so 2 buses or more. So go into your Poisson, do your Poisson CDF. You punch that into your calculator. You're going to tell it that it has 2 and 5/6. You want to go from 2 all the way up to whatever you want. I'm going to put in 10,000, but any number is fine as long as it's big. Remember, you can also do 0 or 1, and then whatever your probability is, subtract it from 1. And hopefully, you should get the same answer I did, which is about 0.775. All right? So we've managed to use expectation algebra and those formulas in order to be able to answer this question about 2 different buses having different distributions being combined. This worked because they were both Poisson distributions. All right. If they're not both Poisson, then obviously you can't combine them together to still end up with a Poisson distribution. But I think one of your homework questions actually did that, where you added 2 Poissons together and still ended up with a Poisson. All right. All right. Great. Let's look at another question. Why not, huh? All right. So here is our next question. We've got some packing boxes. We've got small, regular, and large packing boxes that are being packed up with specific weights. Each one of them, it says, is modeled by a normal distribution. So here we go. We're going to see a different type of distribution here. Okay, 1 full box of each size is chosen at random. We want to find the probability that the large box weighs less than the regular box and 3 times the small box combined. All right. So this is going to be an interesting question here, right? We are looking for, let me write that again, the probability that the large box weighs less than a regular box and 3 times the small box. Why we would want to know that, I don't know, but hey, this is the question we're looking at. All right. So let's see if we can figure that out. All right. So this is an inequality, right? You can rearrange it. So let's do that. We're going to do the probability that r plus 3s minus l is greater than 0, right? It's just an inequality. You can work that out. You can do that algebra, okay? And then or you could do it the other way, right? You could do L minus R minus 3S is greater than 0, and it just doesn't really matter, okay? And so now what we're going to do is we're going to find the expected value of these guys right here, okay? So we're going to find the expected value to find out if it's bigger or less than 0. So we're going to find the expected value of R plus 3S minus L. All right, and the probability that we're going to get, let's see, so that we know then becomes the expected value of R plus the expected value of 3S, and then minus the expected value of L. All right, then we can of course take the 3 out, still doing this expectation algebra. So we've got expected value of R plus the expected 3 times the expected value of S minus the expected value of L. And this we can figure out, right? We can put that straight in. We've got the expected value of R being 12.1. We've got 3 times the expected value of S. The expected value of S was 5 up there. So 3 times 5 is 15. And then the expected value of L is 30.2. And so we get a value of negative 3.1. All right, just like that. Lovely. All right. Now we're going to look at, we also need, of course, in order to be able to do a binomial distribution, we need to be able to look at sorry, not binomial, normal distribution. We also need the standard deviation. So we're going to go through and look at the standard deviations now, but we don't have expectation algebra for standard deviation. We do have it for variance. And so what we're going to do is we're going to find the variance of that number, which is R plus 3S minus L. All right. So that will separate out to the variance of R plus, now remember when I have it multiplied, I could write the variance of 3S, but that's going to be 9 times the variance of S because it is that A squared. And then in the formulas for variance, you may or may not have noticed when we talked about it, but it was not plus or minus. It's always plus because it always stretches it out. It doesn't matter if you're adding or subtracting. This will always add. The variances will always increase together because the positives and negatives can go opposite what we expect. So this will give us the variance of L. All right, and then at this point, we'll go ahead and put each of those numbers in, and we're going to calculate our new variance. So we're going to put in, well, 7 is the standard deviation for the large one. So that's going to be 7 squared, because remember, variance is standard deviation squared. We've got the variance of R, which would be 5, so that would be 5 squared. And then we've got this one, which would be 9 times the variance of S. Variance of S is 2 squared, and then, of course, times 9. And so we get our final variance of the combo, which is going to be equal to 110. All right, you can check that out. All right, so now that I have the expected value and the variance, I should be able to put that into a normal distribution. All right, so that's what we'll do. We'll go ahead and put it into a normal distribution now. Right, we're going to find the probability. So it's a normal distribution. These are all normal distributions. So when we combine them, they're still normal distributions. Okay, with a mean of negative 3.1 and a variance of 110. And so we should be able to put that into our norm CDF. So let's do that. We're going to go norm CDF. Okay, now in the norm CDF, it does ask for the range first. So we're going to go from 0 to 10,000. All right, and then we'll go from a mean of negative 3.1 up to, remember, standard deviation is the square root of the variance, so square root of 110. Your calculator may or may not allow you to put the square root of 110 here. If it doesn't, then you'll need to go out of the screen where you're working with your norm CDF, and you'll have to type in square root of 110 and get a decimal for it, and then put that number in here. 3 or 4 decimal places is fine. And then you should be able to do the norm CDF, and we get a probability of 0.384. Okay, we went from 0 to a big number because we wanted this number to be larger than 0, finding the probability that the number is larger than 0. So we start at 0, we went to a really big number, and we get the probability that they're asking for. All right, so now we will look at the next question, which is letter B, and it says 1 full large box and 4 full small boxes are chosen at random. Find the probability that the total weight is more than 60 kilograms. All right, so this is a very similar situation here, right? I'm going to go ahead and make this a little bit smaller so I got a little bit more space to work. I wish you could do that in your notebook, just kind of scrunch things up, and there it is. All right, so what we're doing now is we're finding the probability that 1 large box and 1, 2, 3, 4 small boxes, sorry, not quite done. We want to show that probability, what is the probability that is, it says more than 60 kilograms, so over 60. All right, so similar situation here, right? First we want the expected value, then we're going to get the variance, and then we'll put those together in a normal distribution to be able to get our answer. All right, so we'll do, we know that first we need the expected value, so I need to take the expected value of all of this stuff is going to be equal, just not looking at the greater than 60 right now, just the expected value of the L plus the large box plus the 4 small ones is equal to the expected value of the large box plus the expected value of each of the small boxes, right? Plus E of small box 4. And we can add all those together. We know that the large box is 30.2. And then each of these is 5, which gives us an expected value for that stuff, our shipment of, so I'm going to just call that X. Okay, the expected value of X is going to be 50.2. And then we'll do the same thing with the variance. So the variance of all that stuff X is going to be the variance of L plus the variance of S1 plus the variance of S2, and so on and so forth. Until we get all of them down there. Then we're going to add them all together. Again, variance is the square of the standard deviation, so we got 7 squared plus 2 squared 4 times. And that will give us a total of 4, 8, 16 plus 49, which is 65, is the variance. And so now I have, putting these together, I have a normal distribution. So X is a normal distribution such that the expected value is 50.2 and the variance is 65. And so now we can go ahead and put that in to our binomes, not binom, and our normal CDF. And when we do normal CDF, we want to show that the value is the probability, find the probability that the value is bigger than 60. So we go norm CDF, and we should then be able to say I want everything from 60 up to however big I want. 99.9 should work just fine. then the mean, and the standard deviation. Remember, your calculator takes standard deviation. This is variance. Calculator takes standard deviation. When you put all that in, we should get our final answer of 0.112. All right, and that's that question. So that gives you an idea of the type of question that you may look at when we're using that the expected value variance stuff. All right, we're going to skip up to